Okay, so we want to look at MOSFET switching in a little bit more detail. So what we're going to do is we're going to go to LT-SPICE to look at what's going on with the MOSFET switching and see if we can understand what's going on. So here is a basic MOSFET switching configuration. We have our power supply, which is right here at the 15 volts, and then we have a control voltage. Now, right now, we're just putting in a control voltage that goes between 0 and 10, and then goes up and down. And so then that should cause this MOSFET to switch between cutoff and triode. So let's run this and see how this looks. So right here, this is our control voltage. So you see it's either 10 volts or 0 volts. And then we're looking at, let's look at the voltage here. So when this one is 10 volts, then this voltage is 0 volts. Let's go ahead and label our gate just so it's easier to see on the LT-SPICE plots. Okay, so when our gate voltage is 10 volts, you see that our drain voltage, you see, is 71 millivolts. So that's much, much less than the gate to source, so it's in triode. So this is when it's a closed switch. If I go over here, you see I have 0 volts on the gate, so now it's in cutoff. There's no current flow. And so then if I look at this voltage, this voltage is going to be either the 15 volts or almost 0. Okay, so this is the MOSFET acting as a switch. Well, if I want to look at the gate here, you see that this is putting out, whenever I switch, it's putting out, let's pull this down here. It's putting out either 2 amps or like -2 or 3 amps. Well, my microcontroller down here can't put out that kind of current. Let's go and look at that really quick. So if I come in and do the ESP32 current, let's see what it can put out. And so the ESP32, you see that it's more on the, we don't, I mean, it can put out pretty high current, but most of the time it needs to be fairly low current. There's lots of things here. See, this one says you can only put out the high current for 10 milliseconds. This one says that it can put out maybe 40 milliamps. Other ones say like 10 milliamps, and so it needs to be down in the milliamps. It definitely can't put out 2 amps. So in order to model this better, we want to keep it safe, so we want this to be in the 10 milliamp range. So we're going to put a resistor here and put in a 1K, and then this is to protect our microcontroller. So now we run this. So now we see that our current's only getting up to 10 milliamps, so everything is nice and safe. Okay, so now we want to look at switching. So basically, when I have a MOSFET, okay, it has some parameters. And so you could get these CISS, COSS, or CRSS type capacitances. If you go and Google it, you can find out that these input, output, and reverse are related to these 3 capacitors. So we have 1 capacitor from our gate to our drain, 1 from our gate to our source, and 1 from our drain to our source. And so for this MOSFET, you see that it has a gate to source of about 2 nanofarads, a drain to source of about 0.8, and then a little bit of resistance between the gate and the drain. So these capacitances are going to limit our switching. So if we look at this switching, so now let's look at these in more detail. So here's our control voltage, and we want to look at, first of all, let's look at our drain voltage. But now we're going to have to zoom in on this transition. Let's start with our upward transition. Let's add another label. So this is our control voltage. So we're looking at our control voltage relative to our drain to source voltage. So right here, when we're transitioning on, so here's where we're turning on. Okay, so what we notice is that first of all, we get a little bit of a lag between the turn on of our control and when this starts to come down. So let's look, and if we look at it in terms of current, it's much easier to see. So my transistor turns on and it just sits there and waits before it turns on. So what's happening? So what's happening is if I look at my gate voltage, that as soon as I turn on, I'm starting to charge up my gate voltage. And so I basically have this big capacitor, and so I get this time constant. So you can kind of see right here that this is the equation for my gate to source. And so it's going to have this time constant, this RC time constant, that's going to be the resistance seen by the capacitor and then the capacitance. Well, the resistance seen by it is going to be this 1 kilo ohm. So if my microcontroller could put out more current, it would switch faster. But we're kind of limiting it here, so that determines what's going on here. Okay, so we're transitioning up, and what's going to happen? Well, let's look at this. So what happens is that my gate to source is going up until it hits the threshold. And so at this threshold point, you see right here, this had a threshold of about 4 volts. And so now what happens is my gate to source is transitioning up. As soon as it hits that threshold, then it's going to start increasing the current going through the transistor. And that's going to cause when the current starts increasing, so if I look at this current, you see as soon as I hit this threshold point, my current starts to go up. And when my current goes up, then this drained source, this blue one, is going to start to come down. Well, the current is dependent on the gate to source voltage. So as these other capacitors are charging and discharging, now I have this drain to source over here, it's going to hold my gate to source fairly constant. So you see in this range right here, my gate to source voltage is fairly constant as my current is, or sorry, as my current is going up and my voltage is coming down. So this is where it's transitioning from active into triode. So right here, in this section right here, we're kind of in active, and then eventually when my voltage gets really small, then I transition into triode. Now we see right here, there's something right here that causes this gate to source to start charging back up. So once we're all depleted, then I'm into triode. When I'm into triode, then my gate to source can start to get going up. Okay, so that is all of this transition, and the goal is just try and speed this up, because if I look at, let's look at the power. Well, if I look at the power, originally down here, there's very little power, and over here, there's very little power consumption in the MOSFET. But in this region is where I get all my power consumption, because if I look at the blue one is the voltage and the green one is my current, right here I have voltage but no current. Over here I have current but no voltage. But in the middle, when I'm transitioning through active, I have both voltage and current, and so I'm going to get this power consumption in my MOSFET, which is what we're trying to eliminate, because that's a loss in the system. It heats up the MOSFET, and this heating that occurs right here is what's going to cause the MOSFET to break and how you lose all of your efficiency. So this is switching, okay? So now let's look so now let's zoom out a little bit. And so we see that then eventually this black one, which is my gate to source, eventually transitions all the way up. And then it's just sitting here, and let's go all the way out. And so now we can look at going backwards. So now we're going the other direction. And so now what is going to happen is going to be the same thing. So originally, I'm trying to turn my transistor off. My gate to source is going to start discharging. When I hit this cutoff point, that's when this current is going to start dropping and my voltage is going to start increasing. So you see that this discharge, the flat section, and then the finish discharging is the same, but opposite for turning off. So I get a power spike for turning off, and I get a power loss in my MOSFET for turning off, and I get a power for turning on. And so these are the transitions. And so the smaller I make this resistor, the more current that I can drive into the gate, the faster it's going to switch, and the lower power I'm going to have, and the faster I can get everything to switch. And that is MOSFET switching.